Welcome to Quantum Computing in Rust, a special topics lecture. So, our goals for today are to learn what a quantum computer is, understand quantum computing fundamentals, learn how to use them in Rust, and know where to learn more. So first, what is a quantum computer? So, instead of normal bits, a quantum computer uses qubits, short for quantum bits. These bits exist in a state between 1 and 0, what you traditionally think of normal bits. They do this by having a % chance of being 1 and another % chance of being 0, thus existing between them, but when you measure them, they're 1 or 0. This lets you use new algorithms that aren't possible on classical computers, thus leading to the idea of quantum supremacy, where quantum computing can reign supreme over classical computing for certain algorithms. But quantum computing is not faster than classical computing, it's just able to do different things. But these different things come at a cost of lots of error, which quantum computers try to mitigate to the best of their ability, but we can never fully avoid all this error. So, why quantum computing? Quantum supremacy quantum supremacy is the idea that some things are only possible using quantum computing. For example, some algorithms are designed for quantum computers and have benefits over classical computers. Grover's algorithm, for example, is an item finding algorithm that finds items in big O of square root n runtime. This means that the runtime scales with the square root of the number of elements in the array. That's pretty much what big O means. It just measures how space and runtime scale with number of elements. Shor's algorithm is a fast number factorization algorithm that runs in O of log n cubed. It runs proportional to the number of bits in the number, which is log base 2 of n. Unfortunately, Shor's algorithm is prone to lots of error, and the largest number right now factored is 21, but as quantum computers get much more error-proof and larger, we'll be able to crack much larger factorization problems, which leads to the scare of RSA and quantum decryption of RSA. So, the fundamentals. First, you must understand electron spin. So, an electron, it has angular momentum. You'd expect for this angular momentum to exist anywhere on a spectrum of values, but it only exists in one of two when you measure when any axis. You can measure spin up or spin down. That's the convention. So, the first people to discover this were named Stern and Gerlach, those are their last names. And what they did was they fired electrons through a magnet to measure the spin. And the electrons, instead of going on a neat spectrum of values, they only went to one of two values. This was the quantized nature of spin that they had just discovered. An electron has a certain probability of being either upspin or downspin, as mentioned earlier by the superposition of qubits. And these electron spin can be defined using two complex numbers. So, complex number can be represented a plus bi, where I is the square root of -1. It's a combination of real and imaginary numbers, and it also can be represented in polar form, using Euler's identity. Electron spin, what you need to know at least, it can point up or down, or can exist as a superposition between the two. And we can represent this superposition as a column vector, where the top value is the probability amplitude, which means when you square it, that's the probability, which leads to a magnitude of 1 when you have probability amplitude. And the z-axis is the convention for defining the basis. For example, down here, spin in the positive z is 1, 0, and the negative z is 0, 1. This is just convention, and that's why everything's defined based upon z. So, qubits. They exist as a superposition of basis states, meaning they're some factor times the first basis state plus another factor times the second basis state. Since this vector must be normalized, that means that the magnitude of this combined vector is 1, which means that alpha squared plus beta squared is 1. And each qubit represents the spin of a single electron. So, superposition, as we mentioned earlier, is how qubits work. A helpful example is Schrodinger's cat, where the cat has a chance of being dead or alive, but you won't know until you measure it. Thus, same with a qubit, you won't know if you'll measure 0 or a 1 until you've measured the qubit and read the result. And it can exist as either one before it's measured. An entanglement, essentially, is that electrons have influence over each other's measurements, so you can measure one electron and know what the other will be, depending on how you've entangled them to begin with. To represent two qubits in an entangled state, use a tensor product, which essentially means that the first element of your first matrix times, matrix is a vector in this case. The first vector times the first element, second vector. First of the first vector, second of the second vector, second of the first vector, first of the second vector, second of the first vector, and second of the second vector. This lets you represent, using two qubits, a bigger array of states, just as you can do in normal binary. So, measurement. Measuring a qubit returns a value of 1 or 0, whether the spin of the qubit was up or down. Up being 0 and down being 1. That's just convention again. There's no, you don't have to label them, but that's just how it's been done in the past, so that's how we do it now. But after you've measured a qubit, it stays at that 0 or 1. It loses its superposition and collapses to the state. So in the Schrödinger cat example, it stays dead after you've measured it, and it's dead. And we can measure this probability using Born's rule, as shown right here. So what this is that, let's say you have a vector that's A times spin up plus B times spin down. And for context, the reverse of the vector, so this notation is called bracket notation, because us physicists are so funny. This is a bra, this is a ket, together, bracket. Wow. And a bra is just a complex conjugate transposed of the original vector of a ket. So this, with the symbol we use for complex conjugate transposed, is a dagger, as you can see here. It's just A conjugate, B conjugate in a row vector. Conjugate just means negate the i's, essentially. And the probability of 0 is the inner product. That's what this notation means, is the inner product of the up vector and psi vector here, your qubit, squared, the magnitude of that squared. So you take 1, 0, AB. That'll just return A, since 1 times A plus 0 times B. Then you square that, so the probability is having up spin is A squared. The probability of down squared is B squared. And since you can only have up or down, that means these two must add up to 1. And as we mentioned earlier, A squared plus B squared must be 1, since the vector is normalized. Okay, now we can talk about quantum gates, which are analogous to classical gates, but let us do different operations on quantum qubits, since they work differently. And these gates can be conditional on other qubits. For example, these are not conditional. These just apply the gate to this qubit and then don't affect any other. But this gate, for example, as you can see, this dot, it reads the value of this without measuring it, and then decides whether to affect this. And this just does with 2. And then these are measurement operators, which measure the qubit, return you the value in this classical register, so normal computing, and then after that the state is collapsed to whatever it measured. Same here, since you also have a measurement gate. So now we can talk about how to visualize these easier. Then we'll talk about it in Rust. So first, the most helpful resource in visualizing is IBM Quantum. IBM.com/quantum, there. Then once you sign in, you'll be greeted with such a home page. And if you want to learn more after this lecture, they have courses and tutorials here, how to use their Python backend, but the knowledge you gain from these courses can be translated to our Rust library later. So, the easiest way is to go here and click Composer, where you'll be greeted, I put stuff earlier, sorry, but where you'll be greeted with an empty Composer here, where you can put in, I don't know why this is still broken, but okay, where you can put in any of these gates, I'll turn on their labels, and drag and drop onto the circuit. So, first, let's start with the Hadamard gate. What that does is that rotates it 90 degrees around. Wait, let me see if I can show you this Q sphere. Oh my goodness, okay. I don't know what's happening. Oh, there we go. There we go. Okay, Q sphere. So what a Hadamard does, I'll decrease the number of. So what it does, this is just probabilities and whatnot. As you can see, it still suffers from floating point errors since it's being run on a simulator right now, but it makes it so it's 90 degrees to the current It's essentially rotated 90 degrees to the current axis, which means that it can be collapsed to either one with equal probability in the z-axis. I'll add some more qubits back, just so I can show you later. Then you have a NOT gate, which 100% NOTs it. So full means 0, or full means 1, empty means 0. Then you can NOT it again and erase that. And Hadamard, you can see it's half-half, meaning the probability of 1 is 50. That's what these what are they called? Phase disks represent. Then you can apply conditional gates, like a C0, where, like, as you can see, this one isn't affected by this gate unless the top gate is a 1, in which case it'll NOT this one. So this, if that one is not, then it'll not. If this one is 1, then it'll NOT this. And you can change which one is the control, which one's the target. Then, an extension to this gate is called the CC0 gate, also called the Toffoli gate. And what this does, if these two are both 1, then it'll NOT, like in this case. And you can use any combination of these gates to build a circuit. The simplest gate is the I gate, which means identity. It does absolutely nothing. Then you can also swap two. As you can see here, I NOT this one, but that one ends up being knotted. Then you can do slightly more advanced gates, like this Rx, which rotates pi over 2 by default around the x-axis, but you can change how much. So I'll change it to pi. That essentially acts like a NOT gate, because under the hood, a NOT gate is a pi rotation around the x-axis. Same with Why? See how it also has a 50% probability? That's because the y gate, or the y-axis, it has the same probabilities being measured into the z just as the x-axis, but the y-axis is imaginary. Then you can do slightly more complicated stuff where it's like dual rotations, but I won't get into that now. Okay, so now how to start in Rust. So there's this crate called QIP, which is a Rust quantum computing library that leverages graph building to build efficient quantum circuit simulators. So, as you can tell, this isn't actually running on a quantum computer. That requires much better hardware, and Rust is not built for that yet. But Rust's borrow checker is a good analog to the no cloning theorem, which in quantum is the theorem that explains that no qubit can be cloned. Just as you would copy something in Rust, you can't do that in quantum. But by default, things will be moved. Things have to be moved, just like in quantum. So, I can walk you through an example here. Let's see this C-swap example. This conditionally swaps 2 qubits, or 2 registers. So it just applies it just applies swap to a number of qubits. Okay, so yeah, as you can see here, 2 registers where n is 3. Non-zero U size you have to use because it won't like if you use 0. That'll give you an error. But first, you must always begin with a builder. This builder represents this quantum circuit over here. This builder essentially lays down the lines, lays down the classical registers, so you can put on blocks to it later. Oh, here. So, begin by doing let q equals b dot qubit. This essentially adds one line that represents q. Then let RA equals register n. That adds 3 lines because that's what you defined n as. So that just adds 3 lines to the bottom. Then here, b.h. This tells the builder to apply a Hadamard on q. And then it saves the value to q. For example here, q is, I'll put some phase disks up here so you can see. So, in the same way, before the Hadamard, q is 100% 0. But after the Hadamard, it's 50. You've reassigned q through the gate. In the same way, this library does that too. Then, you can have a condition here. This works slightly differently from normal conditions, but it's very intuitive. This just says that just as you have this C0 here, it just tells you to read Q as a control. It doesn't ask what to control yet, but it tells you to read it as a control. Okay, if it's 1, you do the thing. So, if it's 1, you swap RA and RB, and then reassign them to RA and RB. Then this is Rust result unpacking. Then cb.dissolve. That essentially just removes the condition from Q. Then you can apply another Hadamard. In quantum computing, gates are unitary, which means that if you apply them twice, they reset themselves. Multiplying a gate by itself is the identity. Then here you can measure, which essentially, just as here you can measure the value of Q, I'll show you here. I'll delete this just to show you how it collapses. You can measure Q, and look, it measures to 1. So it stays 1. But then, oh, there's some more floating point errors. Okay. But you save it to the classical register, which is just your variables in a normal program. Oh, not again. Okay, I'll just close this. Just as you can do that, mhandle is like your classical register, where you can save the classical output of this measurement to, and again, you reassign to Q. Then you just run this circuit with a given precision, which essentially defines how many qubits to use for a certain calculation. Then you're in the measurement chance. You get the measurement from mhandle and have a result. You can run this many times, essentially. That's what it's simulating. Then it measured this with chance that. Result and P. Right here, the result and the probability. Okay, so that was an example of how to use the QIP quantum computing library. If you want to learn more, you can browse the QIP crate, or you can browse their GitHub, Rust QIP. So, in summary, Rust QIP library is a Rust quantum circuit simulator that uses its borrow checker to satisfy the quantum no-cloning theorem. So, thank you for watching, and hope you learned a lot.